Welcome everyone. I am Sri Aravindakrishnan Tyagarajan and I will be presenting our work on lockable signatures for blockchains, scriptless scripts for all signatures. It's a joint work with Giulio Malavolta. Consider the case where Alice wants to buy a TV from Bob and the cost is 1 Bitcoin. Alice makes a cryptocurrency payment by sending a signed transaction that pays Bob to be posted on the blockchain. Consider another scenario where Alice wants to use some service from Bob and Bob requires payment of 1 Bitcoin for every minute that Alice uses the service. In a naive way, Alice will post a transaction every minute on the blockchain. But this is bad for scalability as transaction processing power of the blockchain is limited. Payment channels were proposed as a solution to this scalability problem. Alice and Bob open a channel, which is a shared public key. The channel has a capacity of 30 coins and is set to expire at time t. This means that till time t, consent from both Alice and Bob is required to spend the coins from this channel. After time t, Alice can herself spend the coins from the channel. She does not require Bob's consent anymore. Alice can make payments from the channel to Bob, but none of these payments are yet posted on-chain. Eventually, once Alice stops using the service, Bob can post any of the payment transaction on the chain after generating a valid signature on it before time t. This way, in this example, Alice can make up to 30 payments to Bob with 1 additional coin in successive payments. Now consider another case where Alice wants to buy a TV from Bob. Bob wants 1 Ether in payment, but Alice only has a Bitcoin. In such a cross-currency payment scenario, if Carol and Dave show up, where Carol wants a Bitcoin and is ready to give a Litecoin, and Dave wants a Litecoin and is ready to give a Ether. A chain of cross-currency payments helps Alice pay Bob 1 Ether. This kind of cross-currency payment is facilitated if users have payment channels between them. A network of payment channels that we have in this case is referred to as Payment Channel Network, or PCN for short. Such PCN protocols are possible using special scripts like hash time lock contracts or HTLC. And if you don't want to use special scripts, you have other techniques like scriptless scripts. However, both approaches have a common template as to how the payments are routed through. Parties set up payment transactions that are not yet valid to be posted on chain, and there is a secret key available with Alice. She gives this key to Bob, using which Bob can validate his payment from Dave. This payment validation by Bob itself reveals the key to Dave, who validates the payment from Carol. The same happens with the payment from Alice to Carol. The current state of affairs is such that the HTLC approach is not compatible with currencies that do not have special scripting capabilities. On the other hand, for the scriptless script approach, we only know of protocols that are compatible with currencies that use Schnorr-like signature schemes for authentication. Both these factors exclude a large fraction of existing and future currencies because they do not meet the script requirements. That is, either they do not support HTLCs or they use a different signature scheme to authenticate transactions, like BLS, hash-based signature scheme, or any other signature scheme that does not resemble Schnorr signature scheme. We address this problem in this work. We propose the first generic PCN protocol that has the state-of-the-art privacy guarantees, does not require special scripts, and is compatible with all signature schemes. We also give a highly efficient protocol tailored for the case of BLS signatures that are of immense interest in the cryptocurrency space. As a consequence, we can have a cross-currency payment protocol across all currencies as long as they have the ability to verify signatures on transactions and can verify timestamps on transactions. For example, payments can be made across currencies where a currency supports BLS signatures, a currency uses a post-quantum secure signature scheme, and a currency that uses a hash-based signature scheme. This means that when you develop a new currency, do not worry about including special scripts just to support payment channel networks, because our protocol will work for your currency as well. In the rest of the presentation, I will first talk about why existing approaches fail to extend PCN for all signatures, followed by the techniques that we introduce to bridge this gap. I will give an overview of our generic and BLS-based PCN protocol. We first see why the scriptless script PCN protocol from Malavolta et al. In 2019 does not extend to signature schemes other than schnorr-like signatures. Typically, these approaches have the signatures on the payment transactions to be blinded with some randomness from the sender. The payments cannot be validated yet, as these blinded signatures are not valid signatures. Alice, who has the unblinding key, gives it to Bob, who can unblind his signature and validate the payment from Dave. Using this information, Dave can unblind his signature, and Carol can do the same as well. A crucial factor why this works is because Alice can input some randomness into each of these blinded signatures. However, in some cases like BLS signatures, where the signatures are unique and there is no randomness without the initiation of Alice, Carol and Dave can themselves unblind their payment signatures. And Carol, as a result, can do so for the payment from Alice. This effectively means that Alice has paid to Dave and not Bob. In other words, the payment does not reach Bob. This gives us a clue as to what the missing pieces are. We need a generic blinding-unblinding procedure that does not depend on the structure of the signature scheme. We also need a way for Alice to control each unblinding in the payment path so that the intermediate parties cannot trigger payment release by themselves. We address the first issue at the cryptographic layer and the second one at the transaction layer. At the cryptographic layer, we introduce a new tool that we call Lockable Signatures. We describe this tool now. We have two message key tuples. Both the tuples are input into a lock algorithm that outputs a lock. A signature sigma tilde that is valid on the message m tilde and the lock can be input into an unlock algorithm that outputs a signature sigma that is valid on the message m. We refer to sigma tilde as the locking signature and to sigma as the locked signature. In terms of security, we want hiding. The property intuitively says that the lock reveals no information about either the locking or the locked signature. This is captured via a simulation style definition as shown here. The other security notion we want from lockable signatures is that of unlockability. This property says that an adversary cannot output a correctly generated lock and a valid locking signature such that the unlock procedure outputs an invalid locked signature. We show here the generic construction of lockable signatures based on any signature scheme. The idea is simply to one-time pad the locked signature with the hash of the locking signature as the key. The unlock procedure is similar to the decryption of the one-time pad. The lock in case of BLS signatures is the aggregate of the locking and the locked signature. We can do this by exploiting the structure of the signature schemes as shown here. The unlocking is simply the deaggregation of the two signatures if you know the locking signature. We have weak hiding, which is the search variant of the hiding property of lockable signatures. This construction satisfies weak hiding, following from the difficulty of extracting one of the aggregated signatures only given the aggregate signature. The recent impossibility result regarding BLS signatures and PCN is about building a primitive where we want to generate the lock without knowing the witness. We are able to bypass this impossibility result because lockable signatures are a weaker primitive where to generate locks you need the witness, which here are the secret keys. We deal with the issue of sender control in unblinding at the transaction layer with a new technique that we call local three-party channel. Consider the payment channel between Carol and Dave. They transform their channel into a three-party channel in the following way. They generate a setup transaction that simply transfers the coins from this channel to another channel that is additionally controlled by Alice, who in our case is the sender. To spend from this new channel, Carol and Dave additionally require consent from Alice and therefore the three-party channel. Importantly, the setup transaction is kept local and not posted on chain. With these tools, our generic PCN protocol proceeds in three phases. Starting with a setup phase, where parties establish the local three-party channels with Alice being the third party. We now only work with the three-party channels. We then have the payment log phase, where parties set up payment transactions that spend from the corresponding three-party channels. After this, payment locks are established, first between Alice and Carol. Carol is a user who receives the lock, followed by Carol and Dave. Dave is the user who receives the lock, and finally between Dave and Bob, with Bob having the lock. All the locks are generated via general purpose MPC protocols. More precisely, Alice, Carol, and Dave participate in an MPC protocol to generate the first lock that Carol receives, followed by another MPC between Carol, Alice, Dave, and Bob to generate the lock that Dave receives. Finally, Alice, Dave, and Bob run an MPC to generate the lock that Bob receives. For doing this, we only require MPC protocols that are secure with aborts. We do not require fairness or guaranteed output delivery because if the adversary aborts at any point of the payment lock phase, the honest parties can simply refuse to participate further. This at best results in the lock phase to fail, but the adversary does not get any advantage in stealing the coins of the honest parties in the payment path. And in terms of functionality, the MPC protocols must also internally check the consistency between the locking and the locked signature of consecutive locks. This will be crucial for the next phase. Alice initiates the payment release by generating the signature sigma star with Bob's help. Now, Bob can unlock the payment signature on the payment, and so does Dave, followed by Carol. The payment is thus concluded. To finalize the payment on chain, parties post the setup transaction along with the payment transaction. Recall that the setup transaction was kept local until now. Security of the protocol intuitively follows from the security of lockable signatures. On a high level, there are two attack scenarios. Carol can get paid before she pays Dave, and this is prevented by the hiding property of the locks. The second scenario is that Carol pays Dave but cannot get paid from Alice, and intuitively this is prevented by the unlockability property of the locks. I refer you to the paper for formal arguments. Our BLS-based construction follows the blueprint of our generic protocol. However, the payment lock procedure in the BLS-based construction does not use general purpose MPC. Instead, we give an efficient instantiation, as shown here, for the case of lock generation for Dave. Carol and Bob send their signatures on the respective payment transactions to Dave, followed by Alice sending the aggregate signature, as shown here. Dave can simply compute the lock himself, which is the aggregate of all the relevant signatures sent by others and his own signatures. The computational steps involved are only signing, verification, and aggregate verification, which are the standard interfaces of the BLS signature scheme. Security for the first attack scenario, where Carol gets paid before she pays Dave, follows from the weak hiding property of the BLS-based lockable signatures. For the second attack case, where Carol cannot unlock a valid locked signature, this case is impossible given that BLS signatures are unique with respect to the message and the public key. As you can see, our BLS-based protocol performs quite well compared to the Schnorr and ECDSA counterparts, both in speed and communication. This is because we exploit the fact that BLS signatures are unique, and also that the signatures and the keys can be non-interactively aggregated. In conclusion, we give the first cross-currency payment protocol that is compatible with all signature schemes. This protocol can be viewed as a blueprint to develop efficient protocols for specific signature schemes of interest. Also, the new tools introduced in this work can be used to develop newer applications. Other interesting open problems that arise from our work are if we can have dynamic routing of payments for all signatures, where the sender does not know the intermediaries ahead of time, and also if we can have efficient protocols for other signature schemes of interest. Thanks for listening. Do read our paper and feel free to get in touch with us if you're interested.